very different area. It's a kind of warm up to something else. There's lots of stuff there, so I'm going to just jump through. So I started working 10, 12 years ago with heart modelers in Oxford because they were interested in taking in more software engineering into their work practices. So the basic area is model research in the areas of healthcare relies ever more on quantitative methods. So in the 60s, the mid-60s, Dennis Noble was the first one to write a piece of code that would model the heartbeat of a squid axon. So a very small squid, and he modeled the heartbeat of it. So basically, using differential equations to model this. And obviously in the 60s, this took all night just to do one heartbeat with 4 differential equations. This is what he was doing. Nowadays, you can do real-time computer models of the heart. Why is this important?
I think it's obvious.
Sorry?
It's obvious, I think. Why it's important, it's just obvious for our health and so on.
Well, the reason why there's a lot of interest in this area is because the pharmaceutical companies would really like a heart model that was 100% as realistic as yours or mine. Yeah? Because that means they wouldn't have to do as many animal experiments. Not that they necessarily care, but it requires a lot of time, and they'd be able to get these drugs out sooner, which we'd all kind of like. So there is a big push to try and automate modelling of the physiology. And I was in Auckland where they have Bioengineering Institute, and you'd walk around the building and you'd see various different parts of the body were being modelled. They were doing it in a very engineering fashion. They weren't just kind of worrying about whether they're right or wrong. They just said, this is how this piece of our body behaves. Let's see if we can come up with some equations that model. And then they'd write their code. So these cell models that Dennis Noble worked on was coded in Fortran. Why? Because that was the language of the 60s for doing these things. And right until the late 90s, the best heart model, the one that was in Auckland, one of the Dennis Nobel's PhD students, was still written at its core in Fortran. And had been hacked and optimized and hacked. Now, where's the problem there? Where is the problem?
It's deprecated.
Sorry?
It's deprecated. Deprecated.
Yeah, that's a very good software engineering term. Basically, no one knew what it did. They were writing papers, and they had a heart model which they were pretending, well, not just pretending, they were trying to sell to pharmaceutical companies as modeling a real physiological entity for drug trials. Here were the papers. Here was their code. Yeah? There was a gap. And it was a real problem. So it just happened that Peter Hunter, who's in Auckland, a brilliant academic, late 90s, he hears of XML being developed, and he immediately catches onto this idea, shouldn't we try and write our models in XML? So that then when you would submit a paper with a new heart model, or whatever, eye model, kidney model, whatever, you submit the paper, the XML, and then the conference or the journal can actually try and run the XML and see if it got your results. Because what was happening was that if you take, and you can still do this now, is if you take one of these modelling papers, and it doesn't just apply to heart, it applies to any modelling area, and you try and write your own version of these equations, 30, 40 equations with 20 parameters, assuming you get all of that right, and even if you just put it into MATLAB, what's going to happen is you're not going to get those results. So there's a huge problem. Again, I'm not necessarily talking about jumping in an airplane with the code. I'm talking about you taking customized medicine that's been automatically generated for you based on your physiology. You want to make damn sure that it's not poisonous. So this is the kind of software engineering aspect of this problem. And Peter Hunter realized it was a problem, realized the way forward was using domain-specific languages. A group in Caltech had exactly the same idea. So we had CellML being created and SBML created exactly the same time. So that was the area. So I was kind of employed to look into all of these, into what they were doing, hopefully provide some help. Modeling approaches, there's two, there's discrete and continuum. Discrete is basically like what you would do if you were given a problem and you said, okay, I'll write an object-oriented language. You create objects that will communicate with each other, go around a shopping centre and find out where the best place to put the cheese is so that you buy it. That's a typical kind of discrete event modelling. Continuum approaches are using complicated mathematical expressions. Discrete, we can do proofs on. Continuous, you can't. That is something I quickly learned in this area, is if you replace one function doing something like this with something that does very similar, f dash, trying to say something about this f and that f is nearly impossible. So this is not an area where you can get proper proofs. You just kind of you have to be a bit careful. So domain-specific languages are small languages focused on a particular aspect of a software system. They're not intended for general purpose programming, but to capture a particular aspect of a problem. And in this case, the case of physiological modeling, hopefully it's on the next, it comes up soon. This is what basically the compact version of CellML is. I'll jump straight through it, so it's actually in XML, but the XML is all big and clunky. If you've covered XML, you've seen what XML looks like. Yeah, it's big and ugly. This is basically a compact version of a very simple cell model. So what can you see? Well, basically you've got some definitions. So you've got some variable definitions. It also includes their units. Okay. You might have some initial values that you can use to automatically generate some code from those things in the curly brackets. But basically what's important is the units. And then you have the mathematics, the J and the three ordinary differential equations, which you then have some tool that will run them and be able to give you your model. Back a bit. So there are these two notations built at the same time, CellML and SBML. Both notations have been very successful. You have repositories. So the idea then is you have this notation. Well, let's have a repository, so you can go to cellml.org and you can look at their repository. They've got maybe 1,000 or more models, nicely annotated, that you can go and find out. And then you've got tools for validation and optimization. So there was this interesting problem that they did straight away, is they filled their repository, the CellML guys filled their repository with models. And they made a mistake. And this is where a PhD student of mine came in, but I'll come to that a bit later. There are two kinds of domain-specific language. There's internal and external. What we're talking about here is external ones. External ones are defined like XML. You say these are the elements, these are the attributes. Or if you're using a programming language style, linking back to the previous lecture, you say this is an assignment, this is a conditional, and off you go. And then you have your external. sorry, your internal one is basically when you encode a DSL within a language that's very much done in Haskell. But here we're talking about external languages. So both CellML and SBML encapsulate models as internal components, so they have all these components. They provide a list of biological entities and components that describe biological interactions using equations, real numbers, linear algebra, differential equations. They were initially designed just to be artifacts, not necessarily implementable, but they soon realized because they're declarative that you could actually run these things if you had a numerical solver. So there's a whole range of different numerical solvers for solving different kinds of equations. And again, some are better for certain circumstances than others. But that is the domain of these modelers. They know about these things. What has become quite popular now with these notations is to be able to define, on top of the physiology, is to be able to define a whole range of experiments. And that's done using another domain-specific language, ZML. So that allows these modelers to maybe look at a whole bunch of experiments that you've set off overnight, you come back the next day, and you go, okay, well, this drug in this concentration will work, but not in those concentrations. You might have to run millions, so you can set this all up, and that can all be done on the grid and done quite nicely. All abstracted away, because modelers, this is the point, modelers are only thinking about these differential equations. They don't want to think about how to run these things. They don't want to think about grids, high power computers or whatever. They just want to think about writing mathematical equations. That's what they do. So we want to abstract the different tasks. So XML is a markup language that defines ways of writing these kind of language. It's very simple. You have elements and attributes. This is the stuff you all know about. You can also parse XML documents and make sure they're valid, syntactically valid. But in CellML, we could take it a bit further. So if you have something like this ordinary differential equation, you might write it in XML as follows. If one of you is very astute, you might realize that it actually is using a standard form of writing mathematical expressions inside the CellML one. So this apply, CI, apply times is mathml, which is a way of writing mathematical expressions in XML. It's a standard. So why invent your own standard when other people have already done that? So that's an example of where you have a problem, rather than immediately jumping into coding it in C, Fortran, whatever, you say maybe we should just embody this problem as a DSL. And XML helps you do that. So by separating the mathematics out of the solver, what the Auckland people were able to do was they could have their model in this core ML format, compile it down into C++, link it together with an ODE solver of your choice, and then you could create some runtime code, and with ZML you could even create many of those outputs, which would be run at your discretion in order to solve your experiment. So it's basically bringing the experiment from the laboratory into the computer. That's the idea of doing this. What they also did was some optimizations along the way, which, as I said before, are of this variety. My PhD student spent 2 years trying to prove these correct, and he only could show that they weren't creating problems within certain boundaries. It was quite hard stuff. But what you have the power to do is on the discrete side. You can validate. So you can validate using schemas or relaxing ng. That will validate the tags. That's far better than nothing. You can say, well, this is the CellML document. It has the right elements and attributes. But more importantly, what Jonathan did was he took the units and tried to do something with the units. Why? Are units important? Sorry?
Types.
They're like types. As a programmer, you like types, do you? Why?
Because I use such type systems.
When you write your turn it around. When you write your program and it goes through the type checker, what usually happens?
It says I'm wrong somewhere.
Yeah, but when it works, what usually happens? When it's
A sufficiently strong type system, the program usually works.
exactly. You buy that. You try and tell these modelers that, and they go, "Oh, types are for wusses." That's what they'll say. And you can say, "Okay, what about the Ariane 5 rocket?" You can say, "What about the Mars Explorer that cost millions, crashed into Mars? Why? Because they got the units wrong." You can list a number of disasters that are caused by units, and these people will go, "Units are for wusses." Yeah? How often does somebody in a hospital get the wrong medication? Once a day. Okay? Because of units. A nurse, all good, all well-meaning person, 0.5, 0.5 watt. Yeah? That could be your arse it's going into. Think about that. Yeah? This is what's happening. So units are really important. And Jonathan wrote a units checker. So exactly like a type checker. So this was 10 years ago. No, 8 years ago. At that time, the CellML repository had 600 models. He wrote his units checker for CellML. He applied it to the repository of all the models, 600 models in Auckland. What do you think happened?
Every model except for those you written were wrong.
Well, he didn't write any because he's not the modeler. But you're pretty right, 400 out of the 600 had mistakes. We never published that because we were good friends with the Auckland people. Yeah? But his checker became the de facto standard overnight. Yeah? Nearly all of them were wrong. So this might seem very simple. Yeah? You wouldn't bat an eyelid with this. But you tell a different community, you need this kind of static checker. Because it's exactly the same as a type checker. It's simpler. But they hadn't thought about it because it wasn't in their viewpoint. And it gave a huge hit. Now, fair enough, what they did is filled up their repository because they needed to say, we're serious, our repository is serious. They have to get research money. So they have to say, we've got loads. The fact is, what they had was dangerous. It was full of these kind of bugs.
Show for the previous slide. The problem is that you do not multiply millimeters by millimeters and get millimeters at all.
Yeah. It's a simplified.
Misunderstood. That's it.
They were doing conversions. I'm against conversions. They were, unless you do it coherently, they were doing a lot of strange conversions automatically. So meter, centimeter, multiply by 100. So they were doing some of these code changes. I would prefer to say errors on the basis that it forces the programmer or the modeler to get it damn well right. If they wrote, A goes to B, and this is centimeters, and this is meters, I don't think you should put in divide by 100. This is what a lot of these guys would do instinctively. I would say no, don't put this in. Make the person do this themselves. Don't do it automatically. Anyway, so this is what we developed here. So you can first check that the CellML was correct syntactically, then check that the units were correct, and that's all done. Then we could optimize using some of their techniques, and he got some amazing optimization values by mixing this lookup table thing they were doing with partial evaluation. He got a really good advantage. So brilliant student, brilliant PhD, everybody happy. I have another talk which I won't go into, is I then worked with cancer modelers, and they were doing hybrid modeling. So it was a mixture of the discrete and the continuous. So then I started to say, okay, well, we need to have domain-specific languages which have a lot more features like object-oriented programming. So, okay, let's just start with object-oriented programming and start looking at trying to find patterns in a genuine sense, design patterns, which would be applicable for their models, because I had a colleague who had developed a family of cancer models that he kind of kept refactoring them. So his thing was tumour growth. So you look at how a tumour slowly attaches to blood cells, kills the blood cells, and then the blood cells grow around it, suddenly the tumour grows very big. So he had modelled all of this, and the models were getting more and more complex. I thought, okay, let's use this as a lovely history, and let's develop code that looked at all the various stages and how you could write something that was generic enough that would capture all. So we used object-oriented programming quite nicely to capture those kinds of styles. I was trying to say that hopefully we'd get to a point where we'd have a model-oriented design of cancer, much as what CellML did for very simple cells. But it's something that I kind of stopped doing as I moved from Oxford to Uppsala. But the ideas that I was working on are standard software engineering ideas of high coupling and low cohesion. You know that hear about this very early on in your computer science. You know, high coupling, good, low cohesion. You know, these are things we need. Have you? You've heard these? No? Okay, so what we mean by high coupling is that things are related should be together. So they should be in the class, in an object-oriented terminology. And things that are separate should be in a separate class. High coupling, low cohesion. Most probably Russian equivalent of those terms, that's all it was. These are really important concepts. They do actually work. All of design patterns of refactoring is based on those ideas. So it really does, they really do work. And you can have metrics for these things. So this good software engineering is based on those. Anyway, the other feature of XML is that you've got namespaces. The way they implemented namespaces was horrible. They acknowledged that it was a mistake. They tried to get it out the door very quickly. I think people get very religious about these things. You know, as if you're in a university, you don't need to be so religious. You can just say, okay, that's what XML is. It's not great, but I'll just use it. Whereas if you work for a company that's an XML company, you get all evangelical about these things. So basically, the whole point of the namespace was something they introduced because the predecessor to XML didn't have namespaces. SGML was a predecessor to XML, and it didn't have a namespace. What is a namespace? Well, you hit the problem if we're talking about, have I got it in this slide? You hit the problem if you're inventing documents, this one, yeah. Say if you're covering food and hardware, not hardware machines, but hardware like you find in the hardware shop. Food, you've got pasta, egg, tomato, nut. Hardware, you saw, yeah, drill, nut. We've got nuts used twice. What do we do? Do we kind of, hack and say food nut, hardware nut? But that problem will keep coming back and again. So one way of doing it is by having namespaces. So you kind of do that by attaching it to a non-used URI. We use this very weird way of doing things. So you see these XML documents with lots of these HTTP things in it. You think, God, does this XML go and communicate to the World Wide Web? No, it doesn't. It's just a way of saying this namespace is unique. It's a way of attaching, so we attach food to a potential unique identifier, and you attach hardware to ones. So that allows us then to be able to take two XML documents here and stick them together. So this is, say, double-lined. We're able to have a new XML document, and it might have the double one inside here and the single one inside here, even though you might have names here that are same as names here. And then you can have these overlapping. Why is that important? It's important for interoperability because in this area of developing little languages, we want to then be able to maybe couple these things together. Why? Take the heart example. The human body doesn't just consist of a heart, it consists of a heart and lungs. So if you want to model both, you have to start sticking things together with the blood supply and all the rest of it. But hopefully then we get a whole human body. And when you get ill, when we get ill, doctors can create perfect medication for us that does the least amount of side effects for us. So, pushing this further, what the XML community has is a way of attaching meaning to XML documents using RDF. So RDF is just another XML language that sits on top of your document and will have some metadata. So you hear about this metadata being used. So you hear all about the American NSA going on about, oh, we weren't actually looking at everybody's email, just their metadata. Honest. But we know that they were doing a lot more than that. But when we're talking about the biological community, this metadata stuff is very, very important. Because if you have a heart model, or if you say this is a heart model, this is a cell, you need to actually justify that that's a cell. You need to stick it to an accepted ontology. This is quite new to me, coming from a programming environment where, hey, we just invent we've got a loop. We just say for I is 1 to 10. We just invent I. And we have J and K, and those are kind of standards, but hey, we're kind of chilled about this. If somebody called it I loop, we wouldn't lose our rag. Suddenly you're talking about these modeling communities and you have to use the right names. They get very aggressive. This conforms to this standard ontology. You have to call it this. You have to use this namespace. And I suppose I had to learn that, this is a community. What artifacts they were creating, you have to go along with. Because otherwise, your stuff was just your stuff. It wasn't going to fit in with their stuff. And they were very aggressive. So it's something you might learn. You're chilled out, computer science, programmers. You don't think much of the names you call. Sometimes you'll work with people for whom they're going to be very aggressive. And they're going to tell you, no, this is what the names have to be. Be it in your code, because don't forget these kind of things, these loop things do maybe map onto real things. They're not just code, they might be real things. They might represent real things that people have a meaning. So RDF is one way of annotating your XML document with an agreed upon ontology. Then you have other notations that you might need to be aware of, which are becoming more and more common. You've got Dublin Core. So some of these things are around today, and they'll be changing as time goes on. But the basic ideas are going to be still valid now. This didn't exist in the 60s, 70s, and 80s in programming. Now it exists because we're trying to do lots of exchange, lots of interoperability. You want code to be kind of flying around the world and knowing what it is. So the original motivation for Dublin Core was the way to create ontologies, to add metadata. Simple, very simple tags, nothing complicated. So just things like, okay, this thing, whatever it is that we're going to store in this repository, whatever it is, has a title, has a creator, has a subject, has a description, a publisher, a contributor, date, source, rights. So very much we're publishing information in repositories. So you have to be aware that you might have to conform. Why create your own standard when Dublin Core exists and people expect you to do it? So if you have a document, you might be expected to take something very simple and have this header on top. So this is what people mean by metadata. They mean that has something like this, which by just reading it you can see, okay, Rose Bush was the creator of the document, a guide to growing roses, and a description describes the process for planting and nurturing different kinds of rose bushes. Imagine if it was a description below here of how to grow flowers. Just on its own, you wouldn't know what it was. So this is a standard way of annotating this kind of information. Then you also have a friend of a friend, which again gives an RDF vocabulary for describing people and their relationships with artifacts. So it's being able to publish representations of how one particular person is connected to a variety of resources. So it links people and resources with other people and online resources. So by using friend of a friend within a modelling project, we're able to infer a relationship between the different actors within the repository. So we want to be able to link things. It's not always easy to do that. This kind of modelling area is not easy because you don't always have something simple like FOG, where the outcome of one thing easily fits into the other. We might be talking about blood vessels, how they plug in with other blood vessels. Yeah? Is the flow of the blood going the right way? Is the pressure the right? Is the density the right? There's lots of things that we need to be concerned with. And this is the emerging world of kind of taking code, making it more interoperable. And it's not as easy. So here, a friend of a friend, we just have a very simple example. So I have a friend of a friend here, gives this homepage, and just describes himself. So what he does, his image, and it's basically his metadata for himself. So execution platforms, so this is what I looked at in this cancer modelling, separate cancer modelling project, where they were developing lots of tumour models and they wanted to be able to stick them together. Wanted to stick a top-down with a bottom-up model, if that makes any sense. It was a European model with an American model. That was the purpose of the project. That's why it was big. So you would have a job description language. So this basically harks back to Unix. What you can do by firing off systems using shells and all the rest of it. But it's using it in a more modern way through the means of XML. So you're able to link jobs together using the job description language. And say maybe what machines are needed, what resources are needed, because we're trying to maybe take two different kinds of models, stick them together over different time spaces. One's executing over milliseconds, one's executing over microseconds. So you somehow have to get the two to communicate to each other. This is all big problems that we have. So here we have an example of two jobs that we're linking together. No, this is just of one job. So what this requires, this is a wrapper for a particular job. The job name's run model, application name's run model, and how much resources it would take to be able to run. So then you could have a framework which would be able to decide not just whether the code, but whether the actual job itself was applicable. So this kind of thing was very much used in the Large Hadron Collider project when CERN was trying to work out whether the Higgs particle existed. Because they were shunting, they got money to build a Large Hadron Collider, but they didn't get money for all the data. So it was producing, let's say, a DVD of data per second, and they needed to analyze it. So they needed to fire off all the data and all the processes to various servers around Europe. And it was very much done on this kind of model. In the project that we worked on, we were working on hybrid models. So the models were not designed to be linked, so it was very difficult to make these compound models make any sense. But we kind of did it for the sake of the project. I will say that we did it very well, because there was no agreed way of matching two models together. There was lack of agreed ontology. So they used that to fund a new project. But what we had here was a compound model where we would take two models. So we had the inputs and outputs, and hopefully their types would be consistent, and that is what we used. So we had a compound model, the parameters, EGF, and cell cycle time, and then we had the models that you would try and string together as best as we could. Some of our collaborators had a GUI version that did the same kind of thing. Finally, getting close to the end here, meta modeling is the analysis, construction and development of the frames, rules, constraints, models and theories applicable and useful for modeling. So there's this link between meta modeling and ontology. Meta modeling is very much the UML community. Ontology is very much this biological community. They're doing the same thing. The idea, if you work up the UML stack, you get to the meta model of UML. By creating your own meta model, meaning that your C# or your Java then conforms to that ontology, you're doing exactly what the modeling people, the biological modeling people like. That stuff hasn't quite been articulated very well yet, so there is potential to look at that. So that's what I meant by the different UML models. If you work at UML, typically you're working at the M1 level, writing your class diagrams, and then you've got this M2 level which says what attributes, class, and instances are, and your M3 level is basically the meta model of UML, and just says what a class is like, and everything is an instance of that. So this was part of another European project, is that ZML has been developed, which is a way of defining in silico experiments. So how you can run experiments by writing XML that captures these mathematical models for doing experiments. So this is what Jonathan, who developed the unit checker, is doing nowadays, very successfully. It's a computer-readable format for encoding simulation experiments. The idea being that you just encode the least amount of information and your experiments are generated. Your massively parallel simulations are done all for you, because you don't want modelers to have to think differently. Okay, so I think that's all I have. That's all I'm going to really say for the second talk, which has been maybe more general and less specific, but there's potential for doing work here, but you have to then find a modelling community locally. You have to find people that are doing this kind of modelling. You go, okay, I'm going to automate what you're doing, I'm going to do it really elegantly. Whether you develop an XML format for it or not is neither here nor there, because I think what really excited me when I came across CellML, I'm going to go all the way back to that, was not the CellML. When I looked at those descriptions, they were terrible. It's when I saw this. When I saw this, I thought, okay, it's like a programming language. All these standard programming language tricks and techniques, type checking, which is unit checking, partial evaluation, staging transformations, other kind of optimization we have. And we can give this to that community. There's a lot of low-hanging fruit. So what do I mean by low-hanging fruit? Easy way of publishing papers in this kind of area. But you have to make the effort to meet new people and deal with their eccentricities and deal with their way of doing things. Okay, are there any questions on this stuff? Okay, you're all tired now, aren't you? Yeah?
A little bit.
You can have copies of the slides if that's of interest. I can take them, that's not a problem. And I'll be around for the next 2 days if you want to discuss any potential projects. So if you want to come to me, and we'll schedule slots for the next few days. Okay, thank you very much.